In the previous video, the pre-curve sketching review video, I summarized the vast majority of the points that we've learned so far in chapter 4 before getting to curve sketching that you need to know for analyzing functions in curve sketching. But then I started making the curve sketching example problems, and something else came up that I think could be a point of confusion that I wanted to make a video about and put it here before the curve sketching example problems start. All right, and this has to do with, I want to make a much clearer distinction between what exactly is an endpoint and what is not an endpoint. Or, so what I'm talking about is, we know critical numbers, okay? So with respect to where the first derivative is equal to 0 or doesn't exist, those, you don't have critical numbers at endpoints. Those are away from the endpoints. And it's the same idea with, the official math definition of a critical number is only with respect to where the first derivative is equal to 0 or doesn't exist. But as we go through these videos, I speak about critical numbers with respect to the second derivative. That's not a technical math term, but those are numbers where the second derivative is equal to 0 or doesn't exist. And that's the same exact idea. You don't have the critical numbers with respect to the second derivative at endpoints of a function. It's only away from the endpoints. That's why, we talk about local maxes and mins. Those local maxes or mins, if you're going to have a local max or min, it's going to be at a critical point. If it's a local max or min, then it also is a critical point. That's a theorem. Well, you can't have a local max or min at an endpoint. Okay, and so I thought that this was plenty clear enough going into the curve sketching example problems, but as I started working problems, I realized that I need to make a video here because it can be a little more confusing than I initially thought. So, all right, so the idea is you start with you're given a function, and if you're going to analyze it or do curve sketching, do a full analysis on it, the step that we start with is the domain. We find the domain and the range. But you start with the domain, and commonly the domain is minus infinity to infinity, all real numbers. But we saw how there could be a function where we're just analyzing it on an interval. We did this. This was something we commonly worked with. Something like this. So the domain in this situation is from this x value to this x value, and it would be open here and closed here. So, I'm just going to make something up, but -3 to 5. That's the domain in this scenario. Okay, and so when analyzing a function, when doing curve sketching, the steps are you get the domain and the range, then you find the intercepts, then you analyze for the three different forms of symmetry of the function, and then the next step is you analyze the endpoint behavior. And what we do there is we would take the limit as x approaches, and it would be, okay, for this function would be minus infinity of the function, and see what that goes to. Then you'd also take the limit as x approaches infinity of the function and see what that goes to. For this situation, you would take the limit as x approaches -3 from the right of the function, and you also take the limit as x approaches 5 from the left of the function. All right. Now, one thing I talk about, though, is that depending on the situation, so that might be plenty enough for taking the limit as x goes to plus or minus infinity, but you might want to, for this case, you might want to say, okay, what's the limit as x approaches this -3 from the right of the first derivative, or even the second derivative, because you might want to get an idea of what the slope is coming into this point. It just depends. So, or maybe like for the logarithm, the log of x, the domain here is 0 to infinity. Well, if you take the limit as x approaches 0 from the right of the log of x, that goes to negative infinity. So in that case, you don't need to find out what the slope is coming into this. You don't need to take the limit as x approaches 0 from the right of the first or second derivative. But the limit of the function is fine, and that endpoint is a vertical asymptote, right? So that's the idea of analyzing the endpoint behavior. Okay, and then from there, after you analyze the endpoint behavior, then you get the critical numbers with respect to the first and second derivative, and those numbers are going to be, if there are any, they're going to be away from the endpoints. And if one of those numbers is associated with the first or second derivative not existing, then it's kind of a mystery at what's going on at that critical point, because yes, okay, if you have a critical point where the first derivative is equal to 0, let's say, well, then you know something about that point. You know that it's going to have, it's continuous at that point, and it's going to have a horizontal slope at that point. But if the first or second derivative doesn't exist, and kind of the same idea with the second derivative, you know the concavity could be changing. But if the first or second derivative doesn't exist, well, then you don't know what's going on. It could be a discontinuity. Could be something like this. Could be a vertical slope. Right? So you have to analyze it further. You want to first take the limit as x approaches that critical point from the left and the right and see if it approaches the same value. That's how you can find out if it's continuous. If it's continuous, then you want to see, okay, well, is it something like this, or is it a vertical slope? So you take the limit as x approaches that point from the left and the right of the first derivative, and see if that goes to infinity, so it's a vertical slope, or just see what's going on. Do the same thing with the second derivative. So that's the general process. So far I haven't mentioned anything new. What's this video about? Okay, well, here's another situation. So there's a function that in the example problem videos, the curve sketching example problem videos, here's a domain. We're given a function, and here's the resulting domain. Minus infinity to minus 1, 1 to infinity, not including, so it's all real numbers except for between minus 1 and 1, not including minus 1 or 1. All right, well, this is a little different because, okay, you've got the rightmost and the leftmost endpoints. That in this case, that's infinity and negative infinity. And then away from those, like all the way to the left and all the way to the right, away from those, we've got, minus 1 and 1, let's say. And so the first or second derivative is not going to exist at minus 1 or 1. But those are away from the endpoints. So are those critical numbers? Well, no, these aren't critical numbers. Why aren't these critical numbers? Well, because the function is not defined from minus 1, anything between minus 1 and 1. So if you're going to say minus 1 and 1 are critical numbers, then then 0 is a critical number. 1/2 is a critical number. Minus 1/4 is a critical number, right? So these aren't critical numbers. These, in this situation, minus 1 and 1 are endpoints. These are endpoints. So whenever you get to the endpoint analysis portion, you would analyze these as endpoints. You take the limit as x approaches minus 1 from the left of the function, and the limit as x approaches 1 from the right of the function. And then you might also do that for the first and second derivative, just depending. These are endpoints. These are not critical numbers. Okay, so all right, I guess so. You might be saying, well, I think I kind of already got that. Well, okay, but then consider this. So we work with any kind of rational expressions. Say, here's an example. All right, what's the domain of this? What's this domain? Well, it's all real numbers except not including minus 1 or 3. So the domain you would write as okay, so but it's kind of the same idea. It's not that the function is not defined at minus 1 and 3. I mean, it's the same thing. These are minus 1 and 3 are endpoints, right? Well, no, they're not endpoints. We know that. When analyzing critical numbers, we did a bunch of examples. This is minus 1 and 3 are critical numbers, not endpoints. So what's going on here? Well, all right, this is not a math channel. I say that all the time. This is not for math majors, math PhDs. And so nothing I'm about to say is like official math terminology. This is just my recommendation so to help you to apply calculus, to analyze calculus. But at the same time, you're not going to be everything I'm about to say is going to jive with what the calculus book is teaching you, though, about what's a critical number and what's not a critical number. Okay, this is how you want to look at it. You start with a function. If you're going to analyze it, do curve sketching, you put what its domain is, right? That's the first step. So you can put it however you want in interval notation like this, however you want. All right, you have the domain. You first go as far as you can go to the left and as far as you can go to the right of that domain. Those are always going to be endpoints, whether it's infinity or a single number. Those will always be endpoints. Okay. Now, what about away from those far left and far right endpoints? If you've got a number, if you've got any point away from those farmost endpoints where the function isn't defined, and it's more than a single number bunched together. Like here, it's more than just one. Like here, it's just -1 and that's it. Like this is more than one number, -1 and 3, but they're not bunched together. It's one single number. That the gaps in the domain are one single number. Okay, but if you've got a situation where it's the gap in the domain is more than just one single number, then those are going to be you consider those endpoints. If it's just one single number, then those are not considered. You won't consider those endpoints. Those are actually going to end up being critical numbers every time. Because if the function is not defined there, then neither is the derivative or the second derivative. Okay, and so again, like you have vertical asymptotes here, but it could be anything. You could have a jump discontinuity, or maybe even the function is actually defined here because I have a closed circle, so that wouldn't pertain to this case. But let's say it's not defined. This is still a single number. A single number. The gap in the domain is a single number, okay? So in that case, you don't consider this an endpoint. This is going to show up as a critical number, and you'll analyze it as you'll treat this as a critical number, and the calculus book would define this to be a critical number. So everything I'm teaching you here is going to jive with what the calculus textbook is going to teach you, is the way the calculus textbook teaches it. I'm just saying it's not official math terminology in that, like, you don't call there's no such thing as second critical points with respect to the second derivative. That I made that up, but I think it's just for so you can analyze it to apply it is all. All right. So if you analyze it that way, that you got the far left and the far right endpoints are always endpoints. The far left and the far right of the domain are always endpoints, and then anything away from those, if it's a single number gap in the domain, a single number, then you treat it as a critical point, not an endpoint. If it's a gap in the domain that's more than just a single number, so it's more than one number bunched together, then you treat that as an endpoint. Okay. Then if you do that, the amount of critical numbers you have will all add up to what the calculus textbook would teach. You'll understand, you'll have that distinction between what's an endpoint and what's a critical number, and it won't fail. Okay. So now, and just to point this out too, so there's an example that we work, and I don't say this correctly in the example problem videos, but it's arctangent of x minus 1 over x plus 1. All right. Now, this obviously, so the domain doesn't include -1. It should be, all real numbers except for x is equal to -1. Okay. Now, if you, so that you would treat that as a critical number, right? You wouldn't treat that as an endpoint. It's one single number. So this is why. Now, if you take the derivative of this, it gives you 1 over x squared plus 1. Okay, you plug in -1 here, you get 1/2. So the first derivative does exist at -1. It's equal to 1/2. So it's not a critical point. No. I don't say this correctly. I talk about this in the example problem videos, and I don't say this correctly. For a first derivative, to have a derivative at a point, the function has to exist at that point. If the original function doesn't exist at a point, then neither does the derivative or the second derivative. It doesn't matter what the equation shows. Like you would put, technically, if you wanted to put this first derivative as technically correct, you would say, here's the first derivative where x can't be equal to -1. There's the first derivative. The first derivative takes on the domain of the original function. Same with the second derivative. So this would show up as a critical point with respect to the first derivative and the second derivative. This would show up as a critical point. And it needs to, because if we look at this function, the arctangent of x minus 1 over x plus 1, here's x is equal to -1. You need this you can't have this not showing up as a critical point, because you're going to need to analyze this, right? That's the purpose of critical points with respect to the first and second derivative. It's points of interest. You need to be able to say that this is a point where the first derivative doesn't exist, and so you can analyze what's the limit coming from the left and the right. You would see it's like a jump discontinuity. What's the limit of the derivative coming from the left and the right? And the second derivative, right? You'd have to fully analyze this point. But this would be a critical point, not an endpoint. Okay, and before ending this video, there's one more thing that I want to point out. When you're going through the curve sketching example problem videos, I don't really make this clear. That's one of the reasons I'm making this video here and putting it before the curve sketching videos. But one thing that I continually say in those videos is that, so whenever we're analyzing the intervals of the increasing and decreasing intervals and the intervals of concavity, I continually say that the first derivative can't change signs unless it's across a critical point. And I say the same thing with the concavity. So the concavity or the second derivative can't change signs unless it's at a critical point. And in general, for the vast majority of cases, that is true. But I'm trying to give you the full general scope here so you can feel comfortable in all scenarios. And really what I should have been saying was that the first derivative or the second derivative can only change signs across a critical point or one of these endpoints that aren't one of these middle endpoints like this. So this is not a critical, -1 is not a critical point, but the first derivative or the second derivative could change signs going from, right before -1, going from this interval to this interval. So that would be changing signs across like from -1 to 1, but that's not a critical point. But again, the vast majority of the curves you'll be analyzing, the functions you'll be analyzing or sketching, don't have these endpoints in the middle of the function like this, right? The function will either be defined at all points within the left and rightmost endpoints, or you'll have these points where the function isn't defined at single x values, and those will be critical numbers. So you don't see this very often. But if you do, again, these are not critical points because you've got more than one undefined value bunched together. And the first or second derivative could change signs across these points. But again, the idea would be that this wouldn't be in like -1 or 1 wouldn't be a local max or min. These aren't critical points. This wouldn't be an inflection point. This is not a critical point with respect to the first or second derivative. Okay, so this video should give you a much more detailed, thorough sense of what exactly is an endpoint and what exactly is a critical point for all scenarios, in general, for any type of function. And so with this video and the previous video, which was kind of summarizing the main points that we learned for curve sketching, you should be ready to get into the curve sketching example problems.